Good evening, friends. Usually, I don't make an after dinner video, but today I am making an after dinner video because tomorrow I'm traveling. So I thought that maybe it's a better idea to make the video which I thought of making today. Tomorrow. So one of the viewers had told that he was ready to help me and editing and making my videos look more flashy. I thank him, but he sent an email to me also. But the problem is that I need to have the funds. I don't make money from YouTube. Maybe I should be able to. I don't know where have I kept my where have I kept my mobile? But YouTube has suddenly stated that I have start my videos have started earning something, and it is around $31 I have earned in total or something like that. It's okay. So that's not I'm looking for. So today is essentially a chit chat, an evening chit chat with my viewers, friends, subscribers, non subscribers, those who like me, those who don't like me. It doesn't matter, but here is a channel we are going to celebrate mathematics. Every year there is a kind of I start with a theme. That is what I started from last year. I think I said that okay, let's have a theme on link with physics and mathematics. So we could speak a bit between physics and mathematics. So once a theme is there, that theme, even if we can't say too many things in one go, it will go on. But some additional themes would be added. Uh, so this year, the theme that will come up pretty often is geometry. One of the things that I love. Of course, geometry, Euclid, and the not so Euclid. Euclidean and the not so Euclidean. So we will start talking about Euclid's elements. Actually, I saw in LinkedIn somebody called I nowadays I can't even remember the name. Some Victor Slashov or Klashov, I guess, if I'm not mistaken. Uh, she gives very interesting books actually. So I saw one book and I felt that maybe I should buy it. Lectures on Euclidean Geometry, Volume 1 and Volume 2. Uh, and I saw in the this Google review that it is pretty advanced. Advanced in the sense that elementary geometry viewed from an advanced standpoint. So that's what would be one of our themes here, that we would look at geometry, but from a very different standpoint. Not always, of course, we'll play with the synthetic method of Euclid, where you argue logically and try to prove something. Euclid's elements are here, and we will actually go through them. I have made my board ready in my department, so and I have got a stand and so that I can put my machine, what is that, mobile, and then I'll stand in the board and start explaining things. So many of you might not know that in this celebration of geometry, one of the man we should really talk about is Harold Scott MacDonald Coxeter. Coxeter was one of the greatest mathematicians of the 20th century, rather the geometer of the 20th century, because he revived geometry. In France, there was a movement in the maybe from the late 40s of maybe that mathematics has to be completely brought down from a set of axioms, set of rules, set of logical rules, and geometrically viewing things was a cliche, I mean, in the sense that you should not bother about that geometrically viewing things. That's drawing. Drawing certain things doesn't give you proofs or it doesn't prove anything. Proving something needs the power of just logical thinking. But Coxeter, among them, Coxeter not so there was a secret group of mathematicians in Paris. Alexander Grothendieck was among them, who called themselves Nicolas Bourbaki. So there is a book on the story of Nicolas Bourbaki, and very famous mathematicians were on the list of Nicolas Bourbaki. and they had written volumes on mathematics, Bourbaki's volumes on how mathematics should be presented. There is no geometry there. But Coxeter fought back from Canada, and he exalted in the joy of geometric thinking to the extent that he linked geometry and algebra. That nowadays there's a type of symmetry groups in the name of Coxeter called Coxeter groups, and this name was given by Bourbaki itself, and that is the way he fought against this kind of strange kind of mathematics without visualizing it through geometry, through pictures. And another young boy who fought during those Bourbaki times, whose uncle was also Bourbaki, was Benoit B. Mandelbrot, the father of fractal geometry. So we will start from Euclidean geometry, get into non-Euclidean geometry, and also we will try to talk about uh, fractal geometry, which I learned during my master's degree because I had a project on fractal geometry. So, which was originated by Mandelbrot, which he showed that things that we try to see in the physical world and try to put some shape to them, they do not have that perfect geometric shape. They have a shape which is rough and not so smooth and nice like the normal geometric shapes that we see. And those things are called fractals. Leaves are fractals. The coastline of a country is a fractal. So we will talk about that. I will do it in the board, of course, and talk about fractal dimensions and all those kind of things. So it will be a celebration of geometry year long, and I would enjoy it thoroughly because this is one of the things very close to my heart. Because for me, my path to numbers had been through shapes, and they still rule me. Even if I do optimization and as a research, it is the geometric beauty of convexity that attracts me. Uh, it is geometric interpretation of Lagrange multipliers which is much more important to me than just in shadow price, as economists would like to say. So let us all join in the geometric celebration. For example, I'll show you something. These two-volume books, many people do not know in India, called Kislev's Geometry. Book 1 is plain geometry, plane metry. It's Euclidean geometry. And book 2 is stereometry or solid geometry. So these books was once very, very famous, I think still famous in Russia and the erstwhile USSR, and many of the greatest Soviet mathematicians had learned their geometry from this book. And I do not know, they don't teach such books in India today because we don't do any proofs anymore in India, and we do not do any we don't teach people thinking in geometric terms by trying to prove them. And this is a book on the synthetic approach. Synthetic approach means where you don't use coordinates. When you use coordinates or linear algebraic approach, that's no longer the synthetic approach by simply applying logic. Harold Scott MacDonald Coxeter, in his great fight for geometry, wrote a fantastic book called Introduction to Geometry, which is published now through the Wiley Classic Library. It's a marvelous book, and in one of the finest problems it has, which is pretty fun actually, is the Steiner-Lemmas problem. So if I give you a triangle ABC, and for the angle B and C, the angle which is subtended at B and C, we draw the internal angle bisectors, which meet the opposite sides at some point and intersect at some point. So if the length of these angle bisectors are equal, then can we prove that the triangle is isosceles? It is called the Steiner-Lemmas problem. You may think of it, but it's not so simple that you can say, yeah, there might be somebody brilliant enough to get through it. So geometry is an elementary subject. Elementary doesn't mean it's easy. Elementary only means you need less amount of mathematical tools to handle it. And that's exactly what geometry is. So this book of geometry talks about geometry from the basic Euclidean level, goes beyond Euclid and goes into differential geometry, goes into affine geometry, projective geometry, non-Euclidean geometry, differential geometry, all kinds of geometry. So this book would be one of our major guides as we celebrate geometry in this year. Uh, we will also talk at the end a bit about topology. We will talk, as you said, I said, about fractal geometry, and so we will talk about convexity as convex sets rather, and all these things. And you will see here this book would be one of our chief guides to understand geometry, because one has to understand that there is a lot to learn in geometry beyond your school. In school, what you learn is not Euclid geometry completely. For example, a theorem that most of us learn is if you take a triangle ABC and you take the midpoint of AB and midpoint of AC and join those two midpoints, say at D and E, these midpoints are, and you join them DE, then DE is parallel to BC and its length is half of BC. It's beautiful. The theorem is beautiful. The conclusion is so amazingly beautiful. Uh, but it was not during Euclid's time. I will show you a beautiful book called Geometry, Euclid and Non-Euclid by Hodgson, who is also a very famous algebraic geometer. But there are a lot of books I have in geometry which I want to share with you and I want to discuss with you. Sometimes I'll read from these books as a part of those readings, and sometimes I will actually go ahead and do some problems from those books and discuss certain ideas, especially trying to teach you something about projective geometry. See, projective geometry is an idea that you would need if you want to study things like algebraic geometry. So those ideas will come in. So that I will want to talk a bit more about. So maybe this geometric discussion will continue throughout, but doesn't mean that there will be no other subjects other than geometry. We will speak about some other things, which could be something on optimization, something on linear algebra, something on probability theory, something on statistics. So whatever I find interesting, I'll try to convey to you. There's a lot of questions to me about why not starting actually teaching through this. That would be too extremely tall order because of the too much work that I am involved in. But there is a dream that maybe as I am growing older and going towards my retirement age, 9 years left, I'm 56 and 65, we retire from our services in India. There must be something I should be doing somewhere down the line for younger students, if my health permits, of course, and I'm alive. Of that, both are on a question mark. So then I might actually push forward to have a way to generate some funds where I can actually pay people. Maybe I will try to do it even during this time to pay people to make the videos more nicer, like the three blue and one brown. But that means that person is totally into it. That is his primary job. This is not my primary job, but I'll try to do it in some way. I do not know where the funds will come from, but I'll make a try. So whatever it is, so the idea is to celebrate mathematics. The idea is to make you smile when you look at mathematics books, or read a mathematical concept and feel good. For example, think of a theorem like here is another Coxeter's book, Coxeter and Bourbaki, Geometry Revisit. Wonderful theorems. There is also some theorem of Brahmagupta, our own Brahmagupta, and cyclic quadrilateral, Brahmagupta's theorems. So Brahmagupta has this famous formula. So you know the Heron's formula of a triangle. So if you have a triangle ABC, so which A, B, C are capital letters, the vertices of a triangle. Say I'm speaking to you in English and you try to follow me. You can stop the video and then go stage by stage. So A, B and C a triangle. So now the side AB is marked as small a, side BC is marked as small b, the length, side CA is marked as small c. Then the perimeter of the triangle is the sum of small a plus small b plus small c. and we define a semi-parameter S as A plus B plus C by 2. Now what Heron said, that the area of the triangle is root over a product of three terms, S minus A into S minus B into S minus C. This S minus A in bracket, then into dot S minus B dot S minus C, and you take the root, and most of you know this. Brahmagupta extended this notion to a cyclic quadrilateral. So if ABCD is a cyclic quadrilateral with the sides ABCD, and S is the semi-parameter A plus B plus C plus D by 2, then Brahmagupta's theorem says, Heron's theorem was root over S into S minus A into S minus B into S minus C. Sorry, I forgot that S. Please forgive me. So Brahmagupta's theorem says, I'll not make a mistake, maybe I should say root over S into S minus A into S minus B into S minus C into S minus D. So let me see, where is it? Oh no, root over, no, maybe I'm making a mistake. So it is S into S minus A. Its area is given, is if a cyclic quadrangle has a side A, B, C, D and semi-perimeter S, its area is given by S minus A into S minus B into S minus C into S minus D, right, root. So here we don't have any S, so it's root over S minus A, S minus B, S minus C into S minus D. Now, if one of the sides is 0, then it becomes a triangle. So it becomes S, so your one of your A's, suppose A side is 0. Then it is S into S minus B into S minus C into S minus D. So that is the area of the Heron's formula of a triangle with A, B, C, A, B, D, B, B, C, D. So here is the fun. So there's a lot of fun about doing mathematics, a lot of other discoveries of Brahmagupta. It is a wrong thing to think that our top mathematicians, our ancient great mathematicians like Aryabhatta, Brahmagupta, or Madhava of Sangramangama is not celebrated in the mathematical world. Please get out of that conception. No, they are very much celebrated. Bhaskaracharya, Parahamir, every good mathematician knows about them. So there's a lot of things we should be proud of, actually. We justly should be proud of. But please don't, what should I say? That think that nobody else has done anything in this world. Because I get pushed with these kind of questions in several situations. So, because this is a big world, I want the students who are listening to this to understand this. This is a big world. And every civilization around the world has tried to do something. Some have done something nice. We have done a lot of things nice. And many other people have done things, very different things, and everything has come up into the sum of human knowledge. So nobody denies our contribution to the mathematical world. For example, 0. Just for fun, there was a meeting when I was in the math department, and Professor Kapil Paranjape came from ISER, was a very famous mathematician from India. He came and he had a t-shirt where it was written 0. He said that everyone knows we invented 0, and at the bottom it is written that we knew from the beginning that we are good for nothing. So I think nowadays people would get so angry to see that that kind of, but it was very fun. You are celebrating that you are the country which brought the concept of 0. You have to understand the Greeks, for example, didn't bother about angles. They had no idea about angles, and that came much later. In Euclid's Elements, there is nothing but a right angle. They knew what is a perpendicular. They didn't bother about 60 degree, 30 degree, these kind of things which we learned. For example, the first theorem I learned as a student of the 8th grade was given a line AB and at a point D and a point C outside, join that CD. So the two angles that are made are called supplementary angles. They sum up to 180 degree. This is not a theorem of Euclid. Euclid's first theorem is Very different. And I'll talk to you about the first theorem. And you will see that most of the theorems that are there in Euclid's books, the elements, many of the things you are not never taught at school. And that is the saddest part, that we don't study Euclid. If you study Euclid, not only you get your mathematical sense very well, you get your logical sense very well. Lawyers, for example, though some of you might want to become lawyers or would become great lawyers, should study Euclid. That's one of my suggestions. So geometry is there everywhere. So we would actually study a lot of these things. For example, another book which I love very much is called The Episodes in the 19th and 20th Century Euclidean Geometry. Please understand, 19th and 20th century Euclidean geometry. This is not the geometry of Euclid. Of course, Euclid's geometry, but problems came in the 19th and 20th century. Here also there are discussions about Brahmagupta's theorems. For example, have you heard about something called the Simedian point, or Brocard points, or maybe Siva's theorem and Menelaus's theorem? Maybe some of you have heard about Siva's theorem. Do you know what are Tucker's circles? Do you know the Euler line? Do you know, for example, if I immediately ask you, or do you know the Gauss's proof of showing that if you draw perpendiculars from the vertices to the opposite sides, they are concurrent, that they will meet at a point, which is called the orthocenter of the triangle. How can you prove it? Gauss gave a fantastically superb proof. And in our next lecture, when we start our geometry celebration, we will talk about that. So maybe, and also of course, we will talk about fractal geometry. This is the first, essentially a popular, not popular, but a very beautifully poetic book he has written on fractals. Benoit Mandel wrote Fractals, Form, Chance and Dimension, and after that he wrote the Fractal Geometry of Nature, which supposedly is more famous, but a more beautiful book is Fractals, Form, Chance and Dimension, a book which is not so much well known compared to the Fractal Geometry of Nature. So because fractals, the use of fractals have now come very heavily into finance, because Brownian motion is viewed as a fractal. So the way the price of a stock varies, that sample path is viewed as a fractal, and that can give in more insights into the nature of in the financial market. So this book we will have some readings. It's a beautiful book. It's written in text as well as has numbers. I don't know. I don't know. This is a black and white. This is called the Sierpinski casket, black and white picture. I think the original book must have had colors, and these are just now. It was published originally in 1977, and I got it maybe last year only. So it was very difficult. It was not available in between. Suddenly it is now available. And there is, of course, I have the fractal geometry of nature. And there is also Barnsley's very fantastic book, Fractals Everywhere. And also there's another book called Super Fractals. We will discuss about them, and we can have fun. And Brownian motion, for those who do probability theory, because that is another subject I enjoy. So probability theory has this thing called has an important thing called Brownian motion. It's a type of stochastic process. It is used to build models of price movements in finance. So Brownian motion has a fractal character, and there's a lot of discussion of Brownian motion here. It starts with John Perrine, who had done a huge study on Brownian motion, and so it starts with Brownian motion and gets a lot into the nature of Brownian motion through this angle of fractal geometry. So fractal is a term coined by Benoit Mandelbrot, and we will see more of that. And of course, we'll talk about non-Euclidean geometry. What are the 5 postulates of Euclid? Why they are interesting? Why they are important? Why the 5th postulate is not so much a postulate? If we throw away the 5th postulate, can we build geometry which is consistent? Means where proofs can follow from axioms. And what is truly the physical world? What is the true nature of physical space? So or there's a book called The Shape of Space, which we will come up very soon in one of the things, which is essentially kind of modern combinatorial topology. So we will talk about those things also, about various types of shapes like Klein's bottle. And I do not know whether Klein's bottle I can make, but I can show you how to make a Mobius strip, about orientability, about surfaces, about topological equivalence or homeomorphic objects, similar objects, all kinds of things. Topology will also come, because topology is the, the a very abstract form of talking about geometry. Topology is about giving structure to sets. Because ultimately, if you look at a Euclid's geometry, what happens? It happens in the plane R2. There is always a link between geometry and algebra. Maybe I feel that in some sense, algebra is a kind of language in which geometrical objects are understood. Maybe we will have a better understanding of maths if we appreciate that in some sense algebra is geometry and geometry is algebra. So because you will see the language of symmetry of objects can be best understood through the language of groups. There's a whole subject called symmetry groups. So we will actually talk about the groups, because if you look at geometry, here is a set and there's a group of transformations, and how these transformations are acting on a set is kind of a group action on a set, and that is what properties remain invariant under these transformation, right? So those are the real geometric properties that we want to talk about. So there's a lot of things. Geometry actually opens your mind. It's a floodgate. It's a beautiful thing. I don't know. I can keep on speaking, but I think it's too late, and I think I should say goodbye. Surely next time with much more interesting stuff. Those who love mathematics, subscribe, come along me in this journey, because I have this YouTube channel, because I have to tell you something that makes me go back to my books and read things again, look at things again, and that improves my own knowledge, that makes me think in a different light, and then try to convey my fun and joy to you. Mathematics is a beautiful thing, and people might ask, sometimes I worry now, people keep on asking what I'll do by doing mathematics, what job I'll do. Yeah, that's a question. But by the way, people who are doing mathematics and statistics are nowadays looked up, sought by finance companies, by top banks, by analytic companies, and all sorts of things. And of course, if you want to do academics and you want to keep on doing more mathematics, and that's a very different thing. Or it means you can be working like me as a faculty member and then doing your research and enjoy yourself. Sometimes I feel that maybe, as many mathematicians would say, that they are possibly getting paid for enjoying themselves. See, the whole idea of doing science is to enjoy yourself. The whole idea of doing science is to know what is true about something. So when you make a mathematical statement, why you give up demonstration? So your demonstration is like kind of an experiment, not really experimentation, kind of an evidence that you're providing that yes, these are the reasons for why this statement, mathematical statement, is true. But that our proof has such a beautiful structuring, has such a beautiful solid foundation, that it makes mathematics into such a powerful system, a powerful subject. As in Carl Sagan's book Contact, which later on became a movie, one of the, I think Jodie Foster, who was an actress, who was speaking from a podium. They got some signal from some extraterrestrial civilization, some alien civilization, and she says that mathematics is the true language of the universe. And I also add to it that geometry is the real poetry of mathematics, and we will have a celebration of geometry. Thank you. Thank you very much. Bye bye. Good night.